Oh, yeah. All right, and I think with that, we're going to hand it over to Wolf for our presentation.
All right.
And here you are, sir.
Thanks much.
Special order.
Make sure you got it.
Cafe press.
Cafe press, one of a kind.
No, there's a black version, too.
It does have it. I'm going to start because that way I'll feel like I missed out a lot.
No, what you do is you say, and thank you for showing up.
Jump to the last slide. That's all we have. Oh, I so sure.
I love messing with people.
Yeah, so today we're going to be talking about covert channels, right, which is simply ways to sneak in data, sneak things past IDSs, IPSs. There. Yeah, very sure. All right. So my name's Wolfgang. I got the badge, so I opened the door.
I get your best then.
I don't even open the doors. So I make the coffee, which is good.
Good coffee.
And I hang out with a lot of cool people. A lot of cool people are in this room and learn a lot of good things. I get to write code sometimes, and I get to work with systems. I guess I'm elite.
That what you look like, Shane.
No, what was really a little more realistic is about 80% of my job is actually management. I manage information systems and security. So this is probably a little more.
What was the other one? Your, Match.com profile picture?
No, I'm not putting that one up.
So you have a Match.com profile.
I manage information systems. I manage security for financials. And, people make a lot of assumptions. My name's Wolfgang. You have a beard. Just to clear up some assumptions, everything I'm talking about today, you can always say, I saw that in DEF CON 3 years ago. The things we're talking about are well-known attacks. They've all been invented by people much smarter than me. A couple of them have been explained to me by people in this room, so thank you for that. I'll call you guys out when I get that. Of course, I didn't draw anything out of the Dilbert art. It belongs to Scott Adams, who, if you're listening, Scott, thank you for not suing us. I'm simply here to tell a story about covert channels that explains what they are, some examples of code and whatnot. All right. Before we get to that, we should probably step back and do a little history lesson. Way, way back, long as mankind's wanted to talk to mankind.
When you were 18.
And my beard was black and full. And we hunted the buffalo. And we wanted to communicate, right? We knew we wanted to communicate. So the way communication were explained was A to B, right? Point A needs to communicate to B, A passing a message to B. That's fine. Or if you're in the military, Alpha Bravo, which could get confusing because you won't want to be talking about Alpha Bravo and confuse that with Zombie Tango, which is entirely different. That's so confusing. It's very, very deep. We're going to step away from that for a minute.
Right.
Exactly. Very. So A to B, right? And thankfully, from the time there was caveman into the mid-70s, finally there was an innovation in security in 1978 by Rivest, Shamir, and Edelman. Brilliant people, and they brought us something very fundamental to communications. I'm not explaining cryptography or key exchange or anything. No, it's even more fundamental than that. They're the first ones to talk about Alice and Bob. Thank you. No more when people get confused with Zombie and Tango and Alpha Bravo. Alice send a message to both. But still, we wondered. Who is this Alice? What's her backstory? What's Bob look like? Does he have a match profile? we really didn't know that. So it would be more than an entire decade more before the next great evolution in communications. And that was when Scott Adams started drawing Dilbert. And finally, we knew what Alice and Bob looked like. That made everything so much simpler, guys. And this in IT is what we call progress. So with that, this is the story of Alice and Bob. Alice wants to pass a message to Bob. Very simple. But of course, we're in security, right? So we have to ask ourselves, WWMD. And for those of you guys who don't read Dilbert religiously, may not know I'm talking about MORDAC. You know, what would MORDAC do? What does MORDAC have to say about security and usability? So we really have our captive characters. We have Alice. Alice wants to talk to Bob. Very simple. And MORDAC wants to stop them. MORDAC is responsible for security, and he takes his job very seriously. But then as the backstory, I'm going to walk you through 8 simple vignettes, 8 simple stories. I'll give an overview. I'll show some demonstration. We'll talk about some code as applicable. If you guys want to get deep, I've got the full source code behind this that we can dig into after the presentation. And then I'll give some notes for the attackers and notes for the defenders and things that we can take away from this presentation. And then we'll do a Q&A section. And I mentioned earlier that I'm very fortunate to be surrounded by you guys and everyone in the Michigan community. Very, very smart people. So and when we get to the QA, I'm going to have some questions for you guys. Because I would really like to hear some feedback on what works, what doesn't work. If you saw the security channel on one of your clients and you saw this message being passed forward, how would you block it? What would you do to attack it? You know? So when we get to the Q&A, we'll spend most of the time being pretty interactive. I wrote some .NET code to demonstrate Covert Channels. And then I whipped out, and I'm going to show you guys handouts. Stand up front. Everything is recorded, so I'll be narrating. But with that as an introduction, let's hop into it.
Have the names been changed to protect the innocent?
No, it really is Alice. All the way through. She wrote the code. I just copied them to my GitHub account. Hey, you know, open source. So round 1, we're going to talk about text files. Very simple. Everyone knows change text files. Covert channels can be very, very difficult to stop in a corporate network. Why? Because we've set up our networks to share information. That's what they're set up. We want people to share information, so therefore we create access controls where they can't share. But unfortunately, people can do something malicious with that. We'll take a look at some ways of encrypting. Every single demo I should talk about in this is encrypted with AES, 128 or 256-bit, depending on the length of the message. And then we'll talk about ADS. ADS is a portion of NTFS. It's actually a feature within NTFS that allows you to stuff more data into a normal NTFS string. Usually that was used for properties or systems. But very, very handy because almost nothing can see in ADS. So let's hop into a demo. Let's pray these videos actually work. Ah, yes. So we got Alice. We got Bob. Alice and Bob are on a terminal server. You'll see here when I open up the remote desktop. I'm sorry, Bob. So we have a terminal server environment, which is very common in my organization. People share terminal servers all the time. And we got MORDAC also logged in, and MORDAC's responsible for maintaining the security. Alice and Bob both have user-only access, which means they only have access to folders that they have rights to, such as a shared folder. So a common way of communicating, right? You got your file, you type in your information, and maybe you save it, and you know Bob at his leisure can open it up, and Bob can add comments. And of course, again, this is just normal de facto stuff we do every single day. Except for maybe getting ice cream. I didn't have to do that today. But everything else is every single day. Now, MORDAC, of course, has the same rights. His systems administrator has the same rights to all the same. We can go in, and I'm getting ahead of that. Come on, Alice, good job. So MORDAC can go ahead and, you know, because he's an administrator, he can open up the file, and yeah, we see the file. I don't know about you guys, but I think this is part of the so we want to sneak some information. Now, we can do that a couple of different ways. But for this part, we're going to be talking about data streams. Data streams you can't get to. You can't get to with Word. You can't get to with Windows Explorer. You can't get to, even with .NET. Even though this code is using .NET, we'll talk about it a little bit. I'm actually using Win32 API to do what I'm about to do. So what I'm going to do is, I'm going to browse that same file. Alice puts in the file, she puts in the passcode. You know, she's got a chat stream for herself, and she's got a chat stream for Bob. And Bob will start a very comparable application. These applications are Windows presentation format. So it looks like a normal Windows app. And he's going to browse the file. So within that file, appended to that, will actually be this chat string for Bob, and then another one for Alice here. Now, once they've established this, Alice is talking to Bob, and Bob's talking back to Alice. With this joint communication, Alice can go ahead and type in some messages. These messages are going in as Unicode. That Unicode is then being either AES 128-bit, if it's a small message, or 256-bit encrypted. And it's being passed into that, that portion, that ADS, so that the other chat message can get it. It'll get it, it'll grab it, it'll read it, and run with it. And you can see we're actually incrementing the date modified and some properties in the file. Even though if you look in the file, there's no changes. So what the heck's going on? No, it's fine. Why? What are they doing? Obviously, they're changing something in the file. Within Windows, you've got the ability to do both access control, which allows people to access files, but you also have the ability, and many administrators don't enable it, to do security controls, actually do an audit control. So we're going to enable the audit control. Now, every time that file is touched, it will bubble up to the operating system. We've got to do one more thing. We've got to tell the operating system when that bubbles up, put it in the event log so I can see it. So you do that either in the group policy or the local policy. You can just discuss or whatever. The minute that's applied, immediately, every single time the Allison file writes that folder, that write is going to be logged. What's interesting about that is, before, we knew they were doing something. We could see the date change, we could see maybe the file change, the size change. And yeah, I was just telling a real bad knock-knock joke. You can tell I did this late at night, and I wasn't very sure what to say. But now that they're communicating back and forth, there should be a chair right around if you want to grab one. Or right behind you, maybe. We'll run one. Now, as these changes are coming in, you can scroll through and you can see, look, they ran an executable. They ran some demos. That's pretty interesting. I wonder what they're doing. And you can also see that Alice is indeed writing to some file with colon Alice sets. Now, if you do a dir on the file system, as a matter of fact, if you do a dir in every single OS up until Windows 7 and 2008, you couldn't see ADS at all. You actually had to pull down other executables to see it. With 7 and 2008, listen to me, you know what's going on. You do a /R, there it goes, and you can actually see the ADS. So before, it was really, really had to be doing ADS like 5 years ago. It was really a big song to see you. But now you can do a /R, and you can kind of pull off, guess what's happening. Also, because Alice, maybe like Alice says and Bob says, if you're defending, you're going to go, yeah, I wonder what they're doing. I mean, it kind of like jumps right out at you, right? It's really not very hidden. So one way to hide it is using a GUID. This probably isn't going to fool MORDAC because, of course, he already knows what's up. But most Windows administrators will see a GUID and think that, that must be some system, right? Because GUIDs are usually not generated by people, and it's usually an administrative task. So actually, if you do look through your ADS, you'll see GUIDs on system files where Windows is maintaining a bunch of information. And you're like, that's pretty interesting. And so you can create a new file, and you can use the GUID and talk to it. And by using that GUID, it actually makes it a little bit more covert. It's not explicit. You're not, raising a red flag and saying, hey, look at me, I'm hiding some secret messages here. You're being a little bit more tricky. So we're starting to become a little bit more covert. Even though, again, within that log file, we can still see what's going on. And if you do a dir, /R, still see it. But as you can see, it's got a GUID, so it seems, that must be legit. But he's not fine. So the next thing is, all right, we know we got a Windows form. We know they're passing information back and forth. What can we figure out about this Windows form? What can we do to maybe get some of the data out? Before I get to that, let's wrap up this story. Number one thing that makes interacting with ADS is a namespace called interop services. Interop services, very, very powerful part of .NET. It allows you to pull in COM 132 API. Everything you can execute on the API, you can execute through .NET using interop services. And this is just my code. See, it's very simple. No, all we're doing here is we're writing the file and we're reading the file, getting the size. We have to do all that through interop services because ADS is protected from OS, so it's not within .NET. So attacker notes, if you're hiding, it kind of erases suspicion. Yeah, it's a little bit better if we're in the ADS, okay? So now it's not a text file. That's pretty cool. But if we're hiding in ADS and we've used a handle like my secret stream, and it's going to really leak out at the defenders when it's want to encrypt wherever possible, which makes things much easier. But what encryption ultimately does, kind of like plugging the dam, encryption isn't going to stop the person who's trying to get you. Of course, it's just going to deflect them around, as we'll see, and find different ways to get at you. From a defense perspective, and we talk a lot about this with security information management, you always want to be scanning for the unexpected. If you've got a network share and everything is fine, but suddenly you start seeing a whole bunch of ADS traffic pop up in there, that's probably not normal. I mean, actually, most Windows applications don't write to this area of the file system. The other thing is access controls are not enough. You can't just say, okay, well, we'll prevent them from talking, because our whole reason for having business networks is to allow people to talk. And the minute we've opened that communication to allow them to talk, that's opened up effectively a channel where they can be passing messages back and forth. That's ADS. That's where I'm going to stop for a second. What's interesting about this? What doesn't work about this? What questions do you guys have?
Suggestion.
Suggestion.
When you started out, I know what ADS and alternative data streams are, but anybody who doesn't know what that is not going to get what you're doing. I think you need a little bit more explanation behind that. Sort of like, it's like having 3 data streams that are tied to one file name, but you only see that one file name.
You only see the master string, right?
Then you use normal unless you go through and you do the additional things. That is one thing that I think you're going to catch people with who don't know what alternative data streams are.
That makes perfect sense, yes, because you're only seeing the main stream in the file system.
Yeah. Your demo, very nice, in my opinion. You took it in an area I never would have thought of taking it into. I love that.
Well, I hope it gets better, because that's the boring one.
Oh, well, you got me thinking already on things that's like, I like.
One thing you're not seeing behind the scenes is when that encrypted message gets passed, it'll stay in the ADS only until to the chat channel, pulls it out of ADS. The way the library is written is when Alice sends about a message, about retrieves that message, he immediately erases it.
So there's no logs.
I was wondering why your files were 2 bytes when you had more text there.
Yeah, exactly. So all those 2 bytes say is RxTX. Transmitted with bytes, and then 2 RX. So if you're doing forensics, you can capture that of one message.
And then there was, forensically, there was one other indication that you had an ADS file, is that your file size in bytes and your file size in disk were radically different.
Oh, yeah, I didn't think about that.
In the properties section right
Yeah, that's a very good point.
You do see that the file size on disk.
There is a difference, right?
Well, if you're on a system that has got a very large drive, your sectors or your chunks are going to be very large. So that would hide it.
But that gets to another defense technique, which is know your systems, right? Classic Sun Tzu.
Right, that's the file size.
Right.
Yeah.
Filing, you would see that would be one file that's presented, but if you...
Even when you're talking about a massive drive where they're bumping up the sector size?
Now what you wouldn't see...
He's right. If you have a 64K sector size, you got a 1K file, it's using 64K.
64K.
Right, but then now that'll tell you that you've got between 1K and 64K of data in that file. But
Each data stream needs its own sector.
No.
No.
It's still packed on there, but I believe you'll see that that file is still using more space than you think.
I would agree. I completely agree. That's a very valid forensic technique. And as an admin, too, you should know, right, what you're partitioning.
So 1 out of 1,000.
Everyone in this room.
Yeah, there are only 999 hearts in this room.
Fair enough. So we'll send them the YouTube video. Next thing, all right, so Alice. I've always liked Alice. She's got this fist of death, when she gets riled up. And I can appreciate that. Okay. So we're going to do a little counter-punch here with Alice and MORDAC. Round 2 is MORDAC Strikes Back. 2 things I said in the last section. One is that we're using Windows Presentation Foundation. That is the basic UI map for .NET, allows you to drag on text boxes, fields. The other is that we're encrypting. So encryption isn't going to stop people. It's simply going to make them go around and try and figure out how to break around your encryption. So we'll take a look at what MORDAC might do to strike back. So we got this chat session is already discussed. We've got Alice and Bob. They're going back and forth. There's a tool called Snoop. Snoop is available, freely downloadable. I think it's off Coplex. What's interesting about Snoop is you can actually browse to an application. Here you see we've got Incog open, which is the tool Alice and Bob are using. And they've got the main window. You can see all the different properties of the application within memory live. Not only that, it's not just read, it's read-write. So, for example, if MORDAC wanted to kind of troll them a bit, he could find the title, he could browse in, and he could type in something, whatever he may come up with. It's going to be just as bright as you guys. I forget what to take. But no, the key thing here is a lot of people forget. We can forget when we're dealing with our applications that really there is no security boundary between one application and another in terms of the UI presentation. It all shares a common bus on Windows, which means if you can get on that bus, you can read, write, you can modify, you can really screw with the presentation. You could even go in and take a look at all these messages, for example, because they're already on display, right? It's true they're encrypted and only on disk for just a moment, but we've already decrypted and we're preserving them in memory, so that's great. We can read all the messages. Or, for example, we could go ahead and spoof a message. Again, because it's a common bus inside of Windows. So this tool is Snoop. It's freely available. You can mess with Windows presentation, foundation apps to your heart's content. There's another one that was for WinForm. I think it was called Crackit. That was very popular a few years back. So yeah, we can go ahead and watch what we're doing. Okay, and inject messages into the stream. Just watch to see what else we're doing. The other interesting thing is, and this is something.
What the heck?
Heck? What? Who? So the other interesting thing about this too, and this is something that Larry showed me, is if you can capture the memory, you can get all these messages without even having to do it spoof. If you can capture the memory, you can also get out the password. MORDAC's feeling pretty excited right now. Yeah, rock. Now what Work's going to do is something that Larry showed me. Larry and I sat down. We were at the coffee shop. Big B's. All right, Big B's. I'm like, look, this is great. I created my app, and I've got the secret password. Because in the memory, I'm using a thing in .NET called a secure string. Secure string is awesome. It encrypts it, encodes it. You read the documentation. The greatest thing is the slides spread. I'm like, yes. So I sat down with Larry. I'm like, this is great. You can't read my password. He's like, all right, let's put on this FTK imager, and he's very laid back, of course. And we'll just see what happens. We'll just, look at the memory. I'm like, oh, we can look, but I told you, I read the documentation. You cannot find my password. I was pretty excited about this. But with FTK,
well, if you were trusting Microsoft documentation.
Why did you put up the funny hair picture again? Wound me. So you can pull out all the memory from a VM, and an FTK imager. This is the free one, so FTK, the free FTK imager. You can load up an image file, assuming MORDAC remembers where it is. So MORDAC can go ahead, find the image file, pull it up, and open it. And when it opens, it actually displays all the memory bytes in readable format. And you can do a search. And lo and behold, there's a so anything that Alice and Bob were communicating that they couldn't get from WinForm, you can also just get right out of memory. And the reason for that is, and this is something that Larry and I discovered, is again, because Windows is a common bus, right? It's a bus messaging bus architecture. And you got your form, and you type in your password, you click save, you think everything's good, because now it's saved in this super secure string, which is what's called super string. Mine is called super secure string. Inheritance and all that. But yeah, so you grab it, but by the time it's gotten to there, it's went through Windows forms, it's copied over Windows, it's been leveled up over here, it's over to here, it's over. And we got like 4 or 5 copies.
Yeah, several times over.
Yeah, we found memory. There's a WinForm, and it basically ended up being the way it was being implemented. There's better ways to do it. Number one better way to do it is console apps. So there's also another attack that I'm not going to be demonstrating tonight, which is if you got a hypervisor, these are all external server and it's not Hyper-V. If you got a hypervisor, you can very quickly pause that hypervisor, which will cause the Hyper-V about that is it completely bypasses all the controls. Here we were able to do that because MORDAC is admin. But if you're not admin and you have access to the Hyper-V layer, you can do that and more. I'm not going into this because it's actually a challenge on the upcoming CTF proving site. So when DTOM and Tango are ready to announce that site, this is my contribution to the challenge. You guys can go up and give it a whirl. So some notes for attacker, spoofing, messing with WPF is easy, painfully easy. So when we're building applications, we can't trust the WPF. One of the things I was playing with, and I did demo it here, was the concept of a honeypot, right? So you had a couple different values where they got messed with on the WPF. I assumed that someone was messing with me and shut the app down. I don't know if that may be overkill, but it was kind of fun. Another thing is sensitive information is available in memory, even if you think it isn't. Probably is. So make sure you're careful. Some defense notes is that .NET security has all sorts of, or .NET framework has all sorts of security features. Spirit string being one of them. All the ones we talked about yesterday, lots of different things. But just because it's secure in the documentation, to your comment, don't just go, oh yeah, it's great, ship it. No, we got to make sure we're banging at it and actually going after it as an attack. So any thoughts on that one? Any questions there? No. Going on to story number 3. So from here on out, I think Alice has learned her lesson. She's not going to use WPF. And by switching to a console app, you can't grab all that out of memory. Also, another thing about console app is if you feed a secure string with a console app, the most that's ever stored in memory is 1 character. So just like when we were talking about exchanging messages in memory, where the minute that message is no longer needed, the other chat channel wipes it out, same basically concept. Most you can get on a console app when you're keying in a password, 1 character. Much, much better. So see, from here on out, we're going to be using console apps for Alice. Round 3, some basic steganography. Hidden messages. We're going to be demonstrating the least significant bit. And we'll talk a little bit about that. We're also going to do some reversing that next. As you see, MORDAC's going to run into a roadblock here. He's not going to know what to do. And you get that to the source. So let's do a demo. Steganography is the ability to write into a bitmap file and store hidden messages there. So of course it doesn't have a locate. Every good talk has to have a locate. There's mine. Check that off the box. It's actually on that speaker form, I think, so you can go maybe sign. You can notice that the file size here, you'll watch as we go through that, doesn't change. Also, you notice this has been modified in a couple of years. So yes, she has learned her lesson. She is using a console application. She's going to put in A for Alice. She's sending a message. And she's going to put in a password. It's 16 characters. That would default to 128-bit cryptography. 32 would default to 64-bit. Or I'm sorry, 56-bit. So she also has to put in a number. The number is important because when you're doing basically any messaging, you need to know your start address, your starting point. But definitely for steganography, you need to know what bit you're starting at. Because if you are off even a bit left to right, your message is going to come out, it's not going to match, and therefore, when it goes to decrypt it, it'll fail. Get ugly messages and stay up all night wondering what you did wrong and complain about it in the misec channel. So he's going to go in, he's going to defer reference password file, and boom, there's a message. Great. Now we've got a way files. And MORDAC still has them confined to the shared folder, so that means the security logging and auditing for others still in place, which is good. You can go through and MORDAC can take a look, what's going on, scroll through, what did Bob do? Oh, we ran an application, cleverly hidden by the name bitmap steganography. And see, oh, there is the image. Now notice there's no ADS, so there's nothing fancy there, so it's a little bit more legitimate looking. But when he goes to look at that file, it's a bit confusing because the file size hasn't changed, and neither has the date modified. So that's weird. That could confuse them. one way to dig underneath the covers of Windows is using sysinternals. I'm sure most of us are familiar with sysinternals tools. It's basically the Wireshark of Windows. You can see fundamentally everything that's going on in Windows. Reads, writes, executes, the registry, the file system, system objects, etc. And that's what we're going to fire up next. He's going to start Process Monitor, which is sysinternals' premier tool to have everything. It's a Swiss knife, the sysinternals world. And Alison Bauer still happily chatting along. First Bow goes in, retrieves his message again, putting in his passphrase. In the meantime, while all this is happening, all these messages are still passing back and forth. Thanks to Process Monitor, MORDAC can see those and figure out what's been going on. So MORDAC goes back through and he scrolls through and sees a whole bunch of stuff under here. So eventually it starts to come to a section down here a ways. Keep scrolling. Where the reads and writes of that file have been going on. So it's clear that Bob was reading that file a whole bunch of times, looks like one byte at a time. As a matter of fact, you can see the offset and detail and stuff over there. And when he goes in, when MORDAC goes in and takes a look at the details of these things, sysinternal also includes a copy of the stack. So you can go ahead and see what code was executed. You can see that we've got an incognito library, properly named, and a bitmap steganography. Doesn't look super long. But if he now knows it's being read and written to, it's still kind of confusing. It's being read and written to, then how can the date map message? How can the file sense? MORDAC doesn't get this. So he's going to use this tool called .peek. .peek is one of, I can tell you how many, several .NET disassemblers. .NET is pretty cool in that it's compiled to byte code, which means it's run on a runtime. It's not actually executable. So the flip side of that is cool, it's more secure, memory management, blah, blah, blah. The flip side of that is more insecure. Why? Because all your code is available to anyone who wants to do something like .peek or disassemblers. A couple quick clicks by our friend MORDAC, and he sees, oh, you're doing steganography writes. Click a button. Now I've sped up a couple of these screens because I didn't want you guys to be waiting forever. Up, there you go, file, info. So you see what's actually happening with this function is we are getting the date modified and created when the function starts, writing out our bytes to it, and then when we're done, we're resetting that value so that we can get past MORDAC. So now MORDAC knows. MORDAC's in the know. Now we can do stuff like maybe pull out those bytes, knows the source code, maybe control Alt a little bit by changing the bytes and laughing with the cryptography bytes because it doesn't have all of them. So this gets us to steganography. Steganography, in the least significant, that's very simple. It's just like the old acrostic poems. First letter, means something. And that's what we're doing with this bitmap. We're simply setting the first bit of every value equal the byte of our cryptography. So if you've got 140 character, a tweet size character message. Each character in your code requires bytes. Now you've got 240 bytes to handle. You figure encryption, overhead, and everything, maybe 300 bytes. So you need 1 byte for every bit. So you need about 300 times 8 to have enough space to write your message. Really, still is not much at all. Because of the way the human eye works, at a 24-bit color, changing 1 bit can't know the difference. You can't see it, can't know the printing, etc. And by doing things like messing around with the file, date, modify, etc., it's practically invisible. So it's very easy to create, from an attacker's perspective. Also, from an attacker's perspective, when I have to code, it's very easy to use source code. I mean, 2 collects without peeking. From a defensive perspective, it's very hard to detect. I was looking for some good controls and some good code to demonstrate more like, finding the steganography and breaking it. Cool. But I couldn't help them out. I couldn't find very much. If you guys have anything that you guys see in the field, I'd love to hear about it. Very difficult to find the difference between just a couple of bytes, especially if you're only talking about 300. Always log everything, always. Which gets back to really fundamentally the control for a lot of these covert channels is simply knowing your network and logging everything and then investigating. Of course, if you've got a whole bunch of data, the chance of reading them is very, very small. And that's the end of that vignette. So steganography
way that I know that you'd be able to tell about the file being modified is to use like an MD5.
Yeah, if you did MD5s of all your...
But you'd have to have the MD5 of the original file to know that it changed.
Correct. Or do regular MD5. So if you had tripwire or something, but tripwiring a corporate file server?
Yeah, and who's going to, you know, the amount of time and effort and everything.
And were they really legitimately changing the color of the logcat, or was it for business purposes?
It would have to be something that you would do once you suspect that there was an issue going on.
Correct.
It's not something you're going to do across the corporation.
Correct.
Because nobody's going to do that on an image file.
Yes.
Or like on the KFC recipe file or something like that.
Yeah, change the recipe. Sneak it in.
Oh, you got that too?
Coca-Cola, you got both, huh? Up to 20.
Old and the new Coke. Oh, you want the new one? Want to share?
All right, next up. So let's see what we've done. Cryptography. See, but Alice keeps having the same problem, right? Which is fundamentally, MORDAC came up with a very strong solution in the beginning. One smart solution was simply to enable auditing. Once you've got enabling auditing on a process, you really can't sneak anything past that. You know what I mean? So what Alice has to do is sneak a file past the audit. Now, she's only a user, so she only has access to parts of the file system that MORDAC is allowed her to. So she's got to come up with a different solution. .NET, this so happens, helps us here. There's this concept of a memory maps file, and anyone who's classically trained in comp sci knows this as a mutex. So you take your mutex, grab a chunk of memory, you treat it like a file. What's interesting about that is there's portions of memory in Windows that assumes everyone has read and write access to. So if you can grab a mutex to that portion, you can read, you can write. It's not a file system. There's no ACL to it, so administrators can't prevent it. There's no security ACL to it, so we have no auditing on it. Pretty interesting. It's pretty hard thing to demonstrate. So I'm going to do a lot of walking through here. This is a memory maps file demo. Same basic concept, aids, and in our password. This is using the memory maps class in .NET if anyone wants to Google or check into it and take a look. And it will grab a portion of that memory. First, we're going to put in a name. I should point out. Alice and Bob. That's a great name for the text. And now Alice can type in her message again, Unicode, which is going to be AES encrypted, and we're going to shove it in bytes. But I started thinking, I was talking to Alice, I'm like, if you just put in bytes, it's a whole bunch of encrypted. I mean, there's very low human noise ratio. So it's all data. You know what I'm saying? So what we do here is one extra step. To have a high amount of noise, we're going to use that least significant bit technique. So for every bit of data in this encrypted value, we're actually going to generate a random byte. So we're using LSB within this memory block. Now, MORDAC's, been watching the system. He's checking. So you really can't see anything. You can see that an object handle was created or whatnot. That's really about it. It's kind of like a process monitoring. Okay, yeah, I saw that it ran, but there's another system terminals tool, which is awesome, and that system terminals tool is called WinObject. WinObject will allow you to see all your mutexes. Well, almost all. We'll get to that. Most of your mutexes are available in Windows Object. You can browse. And if you named it Alice and Bob, it's going to jump back out. You can even really secret hidden files. Don't look at me. And if you notice, we have the reference there. The point in it is memory. Once we have that reference and that handle, we can dump it out using FTK Imager, pull it out, and look at it again. Now, granted, we have to go work back through steganography, but it's possible. Now, here's an interesting thing that Alice discovered. She's going to go back. Come on. There you go. Thank you. She's going to go back and she's going to rerun this application. Now, before she used the mutex of Alice and Bob, right? So again, just like we were talking with ADS, that's kind of efficient. You don't want to be using it. GUID is much better. If you use the GUID of the application, which we can default to, there's the GUID. Each application is in Windows given a GUID when you compile it, so it's unique to that application. Windows already is expecting GUIDs, which is pretty convenient. But Windows is expecting GUID. Applications usually use GUIDs when they're addressing their stack in the heap. chit-chatting back and forth, developing MORDAC. And now this is going on through a GUID in the misec. GUID makes memories invisible. Oh, don't give it away. So now when we go in, we do a refresh of the smooth object, and boom, it's not there. Let's scroll up and scroll down just to make sure that I'm not wrong with the symptoms I need. And you'll see that it's no longer present. Why? This is cool, because Windows sees that GUID, is a GUID belonging to the application, recognizes the application GUID very well, most likely as part of the operating system, and therefore hides it. Windows hides it from itself. Windows hides it from sysinternals. Windows hides it from an object. You cannot see that. That is an invisible chunk of memory that we can read and write anything to. The MORDAC's like, hey, what the hell? Of course, we're going to go back to source code. If Alice hasn't learned her lesson the last time when we were doing source code, she's host. You can see, okay, memory maps, doing GUID, yada, yada, yada. What I want to point out here, so you guys can see the difference. As you see all the different objects and the classes and everything. You guys see that? There's English readable text, English readable context. Enter the memory map, blah, 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 blah. And a .NET developer could figure this out. Now, I mentioned earlier .NET is bytecode. That's absolutely true. It can be obfuscated. Every byte can be obfuscated, right? And you can obfuscate in such a way that still is readable by deobfuscating at some level. So there's several tools that will do that, such as Babel. What Babel does, it obfuscates it and sticks a little bit of a header on the .NET app. So the .NET app runs, it deobfuscates key parts, still completely accessible. It still runs the same way. Slightly, I've never noticed any difference, slightly slower. But it's practically unreadable. So to make the deobfuscation or the obfuscation work, simply pulls up the file, takes a look at the settings, just a couple settings that we like to set. I want to click the button. Doesn't like to count yourself. All right. So the first thing is I like to bump the iterations. Iterations, how many times I'll obfuscate it. Default is 3. Find 4 is even a little more confusing. You do 1, whatever. Other thing we like to set is the string algorithm. By default, we noticed a couple minutes ago we could see those strings. We're going to XOR those strings with a value known only to Babel. And so when you look at that code, you obfuscate it, and it'll read it. So boom, she's done it. Now we're going to jump back here to MORDAC. Now when MORDAC pulls that in, Babel out, the other version, there we go. When he pulls that in, he expands it. Look at the difference. Start reading those attributes. Doesn't make any sense. When we scroll down to the string, you see how the strings are XOR byte arrays? Yeah, now we're talking. That's much better. So if we're going to do a covert channel, we're going to sneak some stuff in. We're going to want to use something like a memory map with a GUID, so it's completely unreadable to the OS. We're going to obfuscate the code so that if anyone tries to speak in the code, they can't figure out what's going on. XOR the strings, what the hell? That will get 4 MORDAC. Nice. Game over. Honestly, I think this is as far as I can take this on a local box. If you guys have any ideas on a terminal server when 2 people are connecting, how I can make this even more confusing than MORDAC, I'd love to hear. But I think this is pretty far. We're hiding data among the noise. It's the signal to noise ratio, right? We want a lot of noise. And in this scenario, what we're doing is using least significant bit so that for every byte of data, only 1 bit is actually a value. Everything else is just random junk. We're hiding it in memory using metex. The memory is huge. Most systems have 4 gig. Try finding, less than a K of random memory and making sense of it. And again, we're using it significant. Also, I should point out, it doesn't have to be least significant. It doesn't have to be the 1. It could be 2, 3, 4, 5. We could randomize it. We could put a parameter in there to allow Allison to pick it out to make it even more exciting. Steganography is still hard to detect. We're still in the logging. It's really, I don't know of any way I can make this trickier. So I'm going to turn this around to you guys. How can we make it better?
Question for you. They have a shared password, correct, that they're utilizing for this?
That shared passphrase is the AES encryption. Yes, sir.
Okay, so and you're not using any, doing any salting, correct?
With AES, there isn't necessarily salting. That would be the initialization vector. We could expose that. Yeah, absolutely. We could make that available. They could set that too.
Okay. So if he somehow gets their password, because that's your weakness, sharing the password.
Yeah, exactly.
Then if he ran it at the same time they were running it, would he be receiving what they get?
If MORDAC ran the same time that Bob ran, there would be a race condition to see who would get the message first.
Or potentially each of them get part of the message.
No, if you got part of the message, the code would not erase it. It won't erase it to get all the message. Furthermore, if you only get part of AES, you get a fragment of AES.
Oh, you need the whole thing to decrypt it.
Yeah, it will crash. You get a nice, good exception.
Okay.
Hey, Jim.
If I was analyst, take it a little bit more difficult, right? I mean, you got the cool name of the program, or the executable kind of stands out. And
Yeah.
Process list, you can see that. If I was Alice and Bob, I'd do the Metasploit thing, or the interpreter thing, where I'm running the memory and then I shift the process ID and the antivirus or something like that, or that can look at the
That is a very good point. Absolutely, load it up that way. Or convert your shellcode, load it up by PowerShell. Yeah. No, that's nice. Good idea. That'd be very cool.
Hiding it by using the GUID. Can you do more than one mutex? Just one?
No, just one. I want to come back to his point for just a second. You know, the other weakness to this is we still got that security icon on that folder, right? And really, if Alice and Bob were doing this, they wouldn't put their folder in. They're actually going to folder they know it's being audited. Definitely not. But if it's being passed, such as you suggest, you're launching it from a folder that's not being audited, it's not going to show up in the event log. So that's another advantage.
Yeah. One thought to make it more difficult is to give MORDAC something to chase after that's not there. Use steganography to put garbage back and forth.
Right to the file system. Creating a text with truly random data that they can see.
Yeah.
Alice and Bob, who MORDAC doesn't see the top.
Yeah, things going through and he's trying to break into that. Meanwhile, you're running in this other channel where you're actually sending the information.
Yes, exactly.
Is that or do channel hopping?
Yeah, do text hopping.
So they added two more modules. He said, I was worried he said two more modules.
Hello, thanks for joining. Could you mute your phone, please? Thank you.
Yeah, I was wondering if you could change.
I don't know. Maybe something we'd like to investigate.
I know that.
Yeah, so you get to start a new text and a bunch of stuff.
I know.
You can't get up.
Hello, we can hear you.
Oh.
Everybody else on the conference call can hear you talking. I have a question.
Yeah, hit me with a question.
More towards Terry, I think, because of his background. XOR is not very secure. Have you done any deobfuscation? And how long and difficult do you think that would be?
No, we really haven't had to do much. Usually, when we're doing that, we're actually grabbing it's a Norton's or McAfee that actually will use XORing to take what they have quarantined and doing it, so we can have the true sample. That's, most of the time.
Okay.
But no, what he's pointing out here is just good ways to hide it. Right?
Oh, I just wondered from that aspect how difficult it would be. I'm very impressed.
And I think the point of the XORing is less of securing it, more of just making it more of a layer of work to actually recover what is actually going on.
And I think that's the key point there, right?
or making it take them so long to get it that it's no longer valid and worthwhile.
Exactly. Exactly.
Now, if he finds out that you went out to lunch someplace and talked about him yesterday, there's nothing he can do about it.
Bingo. All right. Stop on to the next one. Now actually get out this side quick. So, MORDAC is sick of this whole terminal services thing. I'm sure you guys are probably getting there too. What we're going to do now is we're going to separate Alice and Bob. So you're going to be on virtuals. We're going to use VDI. So Alice will have a virtual desktop called Alice. Bob will have a virtual desktop called Bob. MORDAC will be either on the management station or Bob. The next one we're going to look at is communication over RPC. RPC, everyone know what RPC is?
It's an easy way to break in.
Very, very easy. Very easy. Very chatty. But you can't prevent it without breaking all sorts of other stuff with Windows, which is the problem. Now, very rare is it the LAN I find that doesn't allow RPC over it. Supplements about RPC go right into .NET, which means Alice and Bob at this point are still user only, and they can run RPC messages without needing any additional privileges, just like they can do with those memory maps. So what we're going to do with Alice and Bob, we're going to use something very similar. Oh yeah, I'm demonstrating. Okay, see, Alice is really on her own machine. See, it really does have a different IP. Nothing on my...
Getting that IP.
No. We can't. So we'll do the demo. And the demo is very similar. You're going to pay to send a message, your passphrase. Now we're going to need to put in a remote IP address, which you're going to have to do, or of course, because we're on the same local box. Now we've got to talk back and forth. What's interesting about RPC is it utilizes the client-server architecture. So Alice, even though she's sending a message, is technically the server. So Alice is going to start a server service, and it's going to sit there and it's going to be listening in for messages until Bob starts his tool, and Bob will connect up to the server and say, hey, do you have any messages? And then Alice can go ahead and type her messages. Again, just like every other demo we've seen to date, this is Unicode that's being AES encrypted, and that encrypted text is then utilizing, in this example, RPC, and simply sticking those encrypted bytes into the RPC packet. RPC layer handles everything else. All the rest of the magic is actually handled by Windows and its underlying API. Very low code to implement this. As you can see, all the other messages are just popping that over. Doesn't it seem a little grainy to you guys?
Yeah.
Okay, so let's take a look. Here's my defense. Let's take a look at Wolfgang adding a video on the fly because he forgot to put it in the stack. Very smoothly distracting from that fact. I'm going to show here on my desktop the MORDAC video for that defense. Now what's interesting about cloud computing in general, let's back this up just a second, is if you remember traditional Wireshark, if you open up Wireshark, you can start on all your ports, right? You guys who do packet captures and the port can just be captured. If you're in a cloud environment, has anyone tried to packet capture off of Hyper-V? I'm the only one crazy on trucks. Okay, you can't.
I'm the only one using Hyper-V.
That too. Like Azure is real fast because it's mine. It's my cloud. So, as we were all laughing, we missed it. No. Okay, so yeah. Within Hyper-V, because of the way the network drivers are built, they're virtual drivers. It means you can't put the card into promiscuous mode. You can't put it in promiscuous mode. It means by default you can't capture up Wireshark. So this creates a huge blind spot for the defense, right? Because if you're in defense and you're doing, for example, everything you do with capturing packets and looking for signature, imagine if you had 4 boxes, right, with Hyper-V running all your servers.
Yeah.
You couldn't see any communication on the last one from one box to another. Completely invisible.
So as the administrator, you want to get into their box and be running your packet capture there.
Bingo. Thank you. Oh, did you? Don't tell me. I don't want to know what you did. So yeah, what we'll do is we'll run, this management station is actually running on Bob. And we'll turn it off for promiscuous mode. And once you turn off promiscuous mode, you can start it. And you can only capture the packet on your box. Now, I want to illustrate here is we talk a lot about signal and noise. And we want to have a lot of noise for a good covert channel. And RPC is incredibly noisy. Look at all this packets. Tons and tons of data. I couldn't even find it, so I kind of cheated. I had Alice display the hexadecimal. Because otherwise, I mean, there's so many, and you get just doing this demo, literally 100 to 1,000 SMP packets, and try and find and match an encrypted string in that. You can't.
The needle in the haystack.
Exactly. And that's exactly what you want. You want the needle in the haystack. Lots and lots of noise, lots and lots of hay, very little needle. So you can see we're trying to go through. Oh, needle, yeah. And they all look the same. They all look identical. It's all an RPC packet with some weird mumbo-jumbo bytes. Someone understands, but not me. So we actually take a few bytes out of this encrypted string and do a search for it. Like I said, this will be a lot easier than trying to browse those packets. There it is. Boom. There is our encrypted message. I'd ask any one of you guys, would any one of you guys recognize this as an encrypted message amongst 1,000 other SMP packets? Yeah, it's going to sneak right by. And because it's encrypted and changed each time, could we do a signature for that?
Ties or something?
That's the exact same size.
Yeah. And I doubt it is that much louder than much more of your standard SMP traffic you see is maybe flow anomaly. That was the only thing I could think of.
Flow anomaly. Well, that's sure, because you're not going to see the response.
Oh, now is normally there going to be RPC traffic between the two devices?
How much more of a delta is this? If it's a significant enough delta that we start seeing flow anomalies above a baseline that we've already captured.
But
right. There's a lot of ifs.
Is there any other RPC traffic between the two?
All those 1,000 packets I just demonstrated?
For between the two?
For all between those two systems.
Was that because they set up an RPC channel, or was that just regardless of whether or not that RPC channel is up?
I think it was because it already established a channel.
Okay. So if there was, now anomalous, this person has never talked RPC to them, now all of a sudden there's this back and forth RPC channel.
That should be suspect from a client perspective too, like your workstation shouldn't be RPC.
Right, directly to another word. Yeah. Right. That would be the only thing I could.
That would be a flag that something's going on, and then you start your investigation.
But so you still wouldn't be any closer to figuring out exactly what's going on. But you now know that something is going.
Yes, that would be control. You know, the countermeasure that controls. There's an SMP redirect message. So you take, to your point, you won't go to the workstation. So you find a file server, and you send two packets. One with an SMP redirect, and one with your message.
Yeah, that's true.
It just bounce it off.
Yeah, now I got to try this.
I'm not RPC the file server in a normal workstation.
Yeah, because you could do that. You could just bounce
around. You'd never see it.
Well, then you'd have to be looking for SNMP read. Oh. I wonder if you could look for the redirects. But then you'd have to know that there was something going on to be looking for them, because you're not going to be looking for them.
Yeah, and again, how many administrators are savvy enough?
If you're in a big enough environment or something like that, it's going to run into the background unless you're talking for
if you know.
Files.
Right.
You think this is a nice cell.
Right. Yeah. And this gets beyond the world of demo. Right? If you knew something was happening and you're MORDAC and you're actually a good responsive security guy, by like the end of demo 1, Alice and Bob would be in HR. Seriously. And this would be a very short presentation. But yeah, so in terms of signals and noise, RPC, very noisy. Very hard to build signature. I like that idea of a two workstation has to trust them. Blocking RPC line, not so easy, right? So next couple of attacks, the last couple that we'll talk about, will actually posit a VPN, or I'm sorry, a firewall between Alice and Bob. So firewalls normally have things open like ping, web traffic, DNS, etc.
But his method of doing the SMB redirect would already be bypassing that because you have to get to the server.
Yeah.
Unless you're on servers that didn't communicate to the
Correct.
other one.
Correct. Absolutely. I'm going to have to. Anyone else have any? We kind of discussed this one already. Okay, good. So Alice has got to get around these technical controls. MORDAC keeps locking things down. We're going to put a firewall in place, and that's going to require Alice to send the messages back and forth, and actually be able to packet capture. With RPC, that's within .NET. You don't need to do packet capture for that. The messaging layer is already there. If you do anything else, like a TCP connection or a ping connection, NAS connection, you need, what do you need? We need to open.
Socket.
Thank you. You need a socket. And unfortunately, sockets were deemed bad by Microsoft many years ago. So to do sockets, you need admin access. There's no way around this. You have to have admin access. We've postulated up until now that Alice don't have it. That's right. They're just plain users. Let's talk about ways to get your group back using shellcode. And I'm going to just demonstrate with .NET how you can execute shellcode. The Incog library that we're demonstrating has some shellcode. There's some simple shellcode and base64 encoding. And within the library itself, we have this shellcode demo. And what the shellcode demo does, it has a couple of different things. Calendar or calculator, which is like the act. Hey, I got a shell, right? So it executes some shellcode and pops up the calculator. It also has some simple shellcode that throw up a dialog box. Yes, malware. And we're going to assume, because that's like the extent of my shellcode knowledge, making that dialog box, that that really does something. So here on out, following along with it, we're going to pretend that actually does something. But in a real scenario, what Alice would be doing is using shellcode to do privilege escalation, to actually bump herself up from normal user up to admin user. And this is all using interop service, like I talked about earlier. And this is what the shellcode looks like. This is the same thing we're talking about, I say, executing shellcode in memory. All we basically do here is we allocate some memory, and then we execute the memory. This block down here, this block up here, this DLL 32, this is all Windows 32 API code. This is standard API code. One place you can get it is from Dan Kennedy, if you ever watched him talk. I actually saw him in Cleveland. I copied this. I wrote down a little test. I think I can do that. So yeah, this is something Dan Kennedy does all the time. Down here is the code that actually executes the shell. So it copies the buffer, zeroes the end of it, and then executes. Very simple. This means is utilizing interop. We can pass shellcode to do privilege escalation. We can pass shellcode to do basically anything you can do with shellcode. The shellcode, like Jeremy was talking about earlier, will bypass security policies or bypass antivirus. Why? Because all the antivirus and everything are actually executed when the EXE launches, not when kernel 32 executes stuff. So you can bypass all sorts of controls and do all sorts of nasty things. Or if you're like me, you can pop up the pattern. So in terms of defense, I mean, running as administrator is a decent speed bump, right? I mean, it's a good idea. We want all our users to run just as administrator. But you could dump password hashes, you can run shellcode. There's a gazillion ways you can go from a user on a box to an admin on a box. I'm sure you could do it in your sleep with one hand magic, blindfold, hanging upside down. Yeah. This technique of
watching it. You've been watching it.
No, I just saw the Bourne movies. This technique is patterned after PowerSplit, which is used in Dave Kennedy's Social Engineering Toolkit. And all PowerSplit does is use PowerShell to launch .NET to call kernel 32 to execute shellcode. Exact same thing we just did here. And against that, like I said, I saw Dave Kennedy's demo and I kind of reversed it. So at a bare minimum, that's one way that Alice can get admin. Questions, comments, thoughts on this one before I flip to the next one?
So that execution in kernel 32, whose memory and use in process space is that actually executing?
The kernel.
So literally at the ring 0, bam.
Well, Windows will
completely outside of interested. Okay, so really privilege escalation is just that.
Yes.
You don't have to jump to a separate, lower ring to actually get your good stuff.
Correct.
Interesting.
Now, if I've got the time, I want to develop this, and I'll probably be talking to a couple people in this room, and I can hear Steven and whatnot, but I want to develop this to actually show the whole thing, all right? So I got my shell code. I execute my shell code. I've got another process behind that process. Now I'm running full head. Right now I'm just copying up an outline, obviously, about as far as I've got it. But conceptually, do that. So we've got 2 more to go, round 7, round 8. And round 7 is going to be pings. Good old pings. Every firewall passes pings. Good old pings.
No, I don't. What thing?
Rule? Lat. Oh, I mean exception.
Oh,
No. A lot of ping is the exception. No. MORDAC means.
now we know how to get to Wolf's network, guys. Thank you.
That's the usual way that likely channels are get for firewalls.
Yeah, it's using ping.
No, ping's ICMP. I'm saying I said DNS.
Oh, DNS. Well, I'll get to that. I'll do that next, just for you. Right now, let's do that.
Change the whole thing just for you.
Yeah. Calls are out to rewrite the constitution. So we're doing, again, this is very, very similar to other demos. You get A and B, Alice and Bob, put in your passphrase to get your message. Now we got to enter in our remote IP address. We also have to enter in our local IP address. That's to build the socket. You got the local IP address to know what address you're looking for the packets. When the packets come in, we're going to pattern match against the remote IP address, and then we're going to pass it on up to some code. In this case, pull out that ping value, read it, etc. Choose pinging. There's also some error checking in here in case the ping packet acts up, because sometimes it does. And of course, you got messages. So from MORDAC's perspective, we're going to go back to using packet capture again, knowing that we would have to be in one of the boxes. We'll do a ping to see what a normal ping looks like. Windows ping by normal or by default is 74 in length and has the alphabet in ASCII, not Unicode, as a payload. The one thing I don't like about this channel is that if you send a message, each message, because of its length, will fit in one ping packet. So we'll send a message sneaking past MORDAC. Message went, you probably saw it pop over here in Wireshark. You see the request reply. You notice that it's a little bit bigger, about twice the size. Because now we've got a message in a payload. You see you got the whole bytes. So the nice thing is very simple to send messages this way. We can send them, Ping will handle it, passes through some firewall. But in terms of signal to noise, it's horrible. I mean, how often are you going to have workstations being back and forth? MORDAC buys it. I don't buy it. I mean, if I'd show this to seniors, like, I just look for anything bigger than 74. I'm going to curve. Because, I mean, it's pretty obvious, you know what I mean, that there's something there. And you've got the full message. It's not segment-graphically protected. So some things we could do here, we could break the message up.
I mean, you can, with ping, you can ping with larger packets if you want, right?
Yes,
I mean,
yeah.
right. So, how do you know that it's not doing that?
That's true.
Testing the connection.
Yeah.
Because 9 out of 10 users don't even know how to use ping.
I read a few seconds.
Okay.
Using random bytes. So we could do a couple different things. We could add noise. We could send out pings, random bytes. We could use steganography. We could create the ping that's on 74 by breaking up the message and different things.
I would just ping in Morse code personally.
Morse code. People that
You don't have to know Morse code.
You only know one person.
Yeah, you write the code and then you're pinging and timing the distance, the interval between pings as your dots and dashes.
Or the length of your pings.
Or the TTL value.
Yeah.
Right. Send 74 for a dot. And send,
75 for a long time.
yeah, 75 for a long. But that would be good. Now I got two things to do.
Or in your payload, since you're doing you can do a standard size, but have 1 byte different for the dash or the dot.
Yeah, I can go back to Morris. Sure. Different ways we can parse this out. Got one more sorted shell where she takes off the head. The last one's going to be DNS. The DNS can pass most firewalls, is what I should hope. We're going with. We're going to do 2 passes. The thing about DNS, with ping we had 1 message per packet, right? If you got multiple packets, we need to have a way to track the ID of those messages and the fragments so that we can reassemble them. If we don't have the right fragments and they're not in the right order, we'll go to decrypt. We'll get a very ugly exception. I won't get this message you won't know that I screen that. So let's do a demo. The first way Alice is going to do this is by separating the message ID and the fragment ID into the host name. So if you think about the host name, it's usually triple dub, but it really can be anything. Matter of fact, the RFC allows up to 255 characters for the host name and for the domain name. Windows, in their infinite wisdom, allows 63 characters in space. I'm not really sure why. I was kind of bummed by that. I want to put more in. But we're going to stick to about 60 characters for each one. Again, we got to put in our IP address, their IP address, open up the socket, do the full connection. Now that we've got that, we're going to execute a message. I wonder why these videos got so grainy.
I know, the first one.
It cleared up one of them. See, this cleared up a little bit. It's MORDAC. No, you hit Steganography message.
Yeah, the message.
That's why it's all blurry.
So you guys see how we've got several different requests. We're actually using NS lookup in this code. Because with .NET, you can use DNS just like ping.
Hey, what are you doing with my domain?
Lucky guess. So with .NET, you can use DNS. It's very easy, but .NET and DNS will only send it to your DNS server on your server, which is really weak. That means you have to change the DNS address of your computer every single time. IP or NS lookup will send to anything. NS lookup also gives you some great feedback as to what it got, and NS lookup will more properly format that value. So what we're doing with this chat channel is we're creating these values, calling NS lookup, batching out to them in the command prompt, and then having NS lookup do all the heavy lifting. And as you can see on the other side, these messages are going across, being reassembled, and decrypted.
You're using UDP,
UDP.
not TCP?
Yes, which means you can have lost messages. That's why we have the basically a container for fragments. It only gets displayed of all the fragments, obviously.
Why don't you just use TCP?
Because I figured DNS over TCP would probably look even more suspicious.
And it may not be as well let up through the firewall.
Well, let off the firewall, and NS lookup doesn't have a command line switch.
I think nowadays most of the people have to do that because you've got like all the content delivery networks out there that use really long strings and you can get a boatload of responses back. So nowadays you're going to be breaking things if you don't allow TCP as well as UDP.
Definitely worth something to investigate. I'd agree. The way this channel works is using base 32 encoding. You can't use base 64, which is the most common encoding that people are familiar with, for 2 reasons. One, there's these 2 pesky characters, the plus and the slash, that don't fit in DNS RFC, which means that lookup won't accept them. If you translate them over firewall will drop them, etc. The other thing that's just kind of annoying is that base 64 is case sensitive. So a lot of different firewalls and different ways of passing traffic would lowercase it, and then the values would be lost. So we're doing base 64, or I'm sorry, base 32, which all the characters are valid, not case sensitive. The only disadvantage to base 32 is, of course, it takes double the amount of characters to base 64, so the messages are a little bit longer. Reasonable trade-off. The problem with sticking it in the, I think someone's going to guess that. That's really ugly. Yeah. That's not going to fly back. But we can't.
But they got to be looking at it before they find it.
True, which is a good point. So if it's box to box within the cloud, you're not going to see it, right, because you're not sniffing within hypervisor. If it's across a network with NetFlow where you're monitoring your Why? Because NetFlow doesn't capture the host name.
Unless they've got something looking for anomalies.
Anomalies or doing full packet capture. Absolutely.
Even if you're doing full packet capture, people aren't going to be looking at the packets.
Yeah, people would have to read through it. Sure, because you also have an amount of noise and whatnot. The way to get around this, one other thing, it can't be encrypted. You guys know why it can't be encrypted, right? The message ID and fragment ID can't be encrypted.
Because it has to be, your character set is limited.
Character set is limited, correct. So 128 bits, usually we need 128 bits of data to encrypt, and then you have this really long listening. So we can't really encrypt it, and of course there's multiple different values.
Why couldn't you use something, granted it's cracked, but something like RC64 or the Enigma protocol that would just be...
As long as you're only encrypting a very small space, and then encode and being able to have that one encrypted value per message you can go.
Route 13.
No, that's what I'm saying, is that if there's a predetermined, essentially, well, actually, one-time pass would also work. If you had to set the one-time pass on either side for base 32.
Yeah, exactly.
Then it could still be encrypted, and then there basically be no way, like, say, reverse engineering the pad, which is essentially impossible.
And
Unless they're cheating at bingo.
that's what you figure.
Thanks to my right cryptonomicon, too.
The basic 32 implementation, the stack, is actually an overridable array for that very reason, that you could create your own array on a one-time password and have your own encoding using 32 characters, any character you want. So yeah, absolutely. That'd be fun. The way
There goes the rest of your weekend.
The way that we got around this, what Alice ended up doing was separating the encoded value, the message ID and the fragment ID, the encrypted fragment, and using something very similarly significant that we're actually overriding values. Be very bad. You don't want to override a value in encryption. You know, human eye may correct that, AES not so much. Instead, what we're doing is taking that base 32 character, base 32, 5 bits. The first bit, bit 0, on a base 32 pair, is going to that message ID and that fragment ID. Now we've got one bit up, all across the entire array that contains the message ID and fragment ID encoded. And the other 4 are going to be for the encryption. I'll show you what that looks like. It'll look pretty much similar to what you guys saw before, except it'll be www, the host name, because the characters that are in the domain name are now including an encoded fragment ID and message ID and an encrypted fragment. We have our IP addresses. Boom. Transmit our message. Oh, I guess. That kind of helps if someone's listening. I actually get bored of that. I'm just going to skip the screen. I'll show you. So what it ends up looking like, yeah, I was kind of exceeding my patience, so I'm sure it's exceeding yours. What it ends up looking like, here's a message, and here's the values. And you see www, and we have our encoded space. And it works very well. One weakness that MORDAC may pick up on is that in doing this, remember when we were talking about the file size, you have 1 byte for every bit. It means the file size has to be so long to contain the values. But we'd have to pad out sometimes the fragments to make sure there's enough space to include the message ID and fragment, which means you start ending up things with lots of A's at the end. That's not too cool. I mean, maybe he'll catch that, maybe he won't. I didn't like that. So instead of doing that, what we actually created was a random byte space first. And then within that random byte space, populate it with the encrypted bytes so that these values will always have something. So you see the difference from 1. I can go down just 1. 2. Okay. So you guys see that way the value is changing. What's also nice about this is not only now with the message, the last value will be a little bit harder to figure out what's going on, but now the host name will always be changing. Each time it's run through, randomized, a new base value that these byte arrays are blended together. Oh yes, this is good. As long as but one port is open, we will find a way. I found it very inspirational. Okay, so in the background you see we've got our packets being captured. Here's the These are completely valid, completely normal in every single way DNS packets. There's nothing unusual about the DNS packets. They're being created by, and as slick as I mentioned earlier, the only thing that's been strange is they've got this very, very weird looking pussy. But they're encrypted and coded bits. So as we were talking about earlier, from an attack perspective, DNS passes most firewalls. A smart, savvy firewall administrator would perhaps only allow DNS traffic to go to the DNS server as opposed to letting it go between two workstations. Obviously, that's kind of a weird look. But there is a well-known software package called Ozyman DNS. We actually load up what looks like a very valid DNS server out on the web, and you can load up a client on your box. It uses a very similar process using base-32 encoding, tunnel all your IP traffic right on out. So it's a well-known attack. It's out there.
What was the name of that application again?
Ozyman DNS.
Yeah, that's one of the
And
right?
And it's Kaminsky?
Yes, sir. My hat's off to him for showing me how to do this. So some possible defenses we've talked about is I was doing full packet capture. Filtering DNS requests without response. It's pretty weird if you see a whole bunch of DNS requests going out with no responses. Now, we could fake responses back. That'd be easy enough to do in the Bob side of this application.
You go to a big enough network to find somebody who's got their DNS configured incorrectly. At least one of them, or one device that's down, so you're going to see that stuff.
Exactly. It's a matter of how much noise you want to generate. Some other ways to make this more exciting is to roll out other DNS queries. So maybe the message space is 4 DNS messages, but you send out 6, 2 which are randomized. Randomly sending out the messages in no particular order. Right now they're going out sequentially, but they could be completely randomized. Because on the Bob side, the application is putting it back together anyways in the right order. Different ways we can generate more noise, more excitement. Any thoughts on DNS before I flip to the end of this? All right. So the end. Hooray! Not really. There's a lot of other different things that are available in Covert Channels. Lots of other different ways we can play with this. Covert Channels, I've been having a lot of fun. So if you're interested in those sort of things, I definitely encourage you to look into it. The ones we look at today are alternate data streams, which is a feature within TFS. Least significant bit, which is the classic way of doing steganography on images. Memory mapped files, which is a very fun way to put a whole bunch of data up in memory requiring no access controls and completely worth investigating. Windows RPC messaging, ping messaging, and DNS. Fundamentally, if you think about it, everything software and all software does is read bytes, parse bytes, execute bytes. What that means is that every single byte channel, everything that we built our computers to do, is effectively a covert channel. You can put covert channels in anything. It's wide open. And beyond it, Bob and Alice, what could this be used for? Destroying botnets, appropriate espionage, bad things. This is only messaging just because it's fun, but it could be used in other ways. So I thank you guys all for listening. This is my summer project. My daughter was out of town. I got off at 12.
That's where we told you next one.
I ran clock. What?
I said, is this where we tell them that they've actually been doing their real communications over Twitter?
So, I thought you put that on flight. I actually got a cool demo of the 37.2, which and I are working on.
Oh.
Yeah. Using location.
Oh.
Yeah, I saw that. GPS, I mean, everything it's bytes and strings is a channel. So when I was playing around with some code, it ran clock, and I ended up with like 50,000 lines of code I wrote this summer, which is like insane, and most of it didn't work, but it was still a lot of fun. At about the time, Zombie Tango and I started talking about putting this together as a talk, I had maybe about 7,000 lines of demos that barely worked. And what I've showed you today clocks in around 4,000 lines. So it's getting tighter, it's getting better. And Tom and I are going to be doing some play, see if we can build signatures to detect these things. Come up with some new ways of having some fun.
Create a new botnet.
Great and bad.
Yeah.
We're moving to
Yes, yes. That's all I got. Thank you guys very much for your time tonight. Appreciate it. It's been fun. Thank you for the ideas.
Thank you.
Hey, Wolf.